So let me invite for the next talk Professor Ofer Aharony from Weizmann, who will tell us about the complex relationship between string theory and quantum field theory and vice versa.
Okay, so I'd like to thank the organizers for putting together this conference and for inviting me to speak here. So I first met Yuval Ne'eman when I was 8 days old, because my father was his graduate student at the time, my father Ofer Aharony, and he came to my Brit. So I met him for the first time there. And my father Amnon asked me to send his apologies that he could not come here today and give a talk to himself for personal reasons. But he did send me this picture where he's sewn together with Yuval and with Michael Fisher. This was many years later after this event. Anyway, after my Brit, for many years, I did not meet Yuval, but as a teenager, like many Israelis, I read his popular books on particle physics and on quantum physics, and possibly they influenced my decision to later go into this field myself. And then many years later, when I became a graduate student in particle physics, Yuval was just coming back from politics to Tel Aviv University. And I had the opportunity to attend a course that he taught where I learned many interesting things about physics and even more things about the Jewish heritage of various physicists, which was one of his favorite topics at the time. So anyway, 40 years ago, there was a similar conference which Yuval attended for his Yuval's 60th birthday, whose title was From SU3 to Gravity, and which tried to cover all of Yuval's research interests, ranging from quantum field theory to quantum gravity. And in my talk today, I'll try to give an update on what's going on with these topics now 40 years later. So I'll give a very brief review of quantum field theory, which will be much more basic than what was in the previous two talks. I'll then give a brief history of string theory, which is our leading candidate for a theory of quantum gravity. I'll describe various relations between them and how we put them together, and I'll end by summarizing their current status and to what extent are they rival theories or duals. So let me begin with a very brief review of quantum field theory. So quantum field theory is what we get when we unify quantum mechanics with special relativity, and it is also almost 100 years old by now. The basic objects in quantum field theory are local fields, phi of x, which appeared in many of the previous talks, where x is some point in spacetime, and phi should be thought of as some analog of the electromagnetic field at that point. But in the quantum field theory, this phi becomes an operator, like many things in quantum theories, which describes some local degrees of freedom that live at every point in space. One way to describe a quantum field theory is by starting from the set of fields, phi I of x, and by their interactions that have to be local for the consistency of quantum field theory. So typically, the interactions that we write in the Hamiltonian or in the action are composed of various local terms like this, where we have a product of some fields at the same point, and we have some coupling constant g. Now, in the limit where these coupling constants go to 0, we get a theory of free fields, and free fields turn out to be just the same thing as free particles. So a free field theory just describes free particles. And then when we turn on small values for these couplings in perturbation theory, we have some interactions between these particles, which we can compute in perturbation theory, and we obtain Feynman diagrams like this one that tell us how to compute the interactions between these particles and fields in perturbation theory. However, quantum field theory is well defined also at large values of the coupling. So for those values, we cannot use perturbation theory, but we can use other methods like computing the path integral of the quantum field theory. However, most quantum field theories are much more difficult to study at strong coupling, and in many cases, we have to resort to numerical simulations, say of just numerically computing this path integral. It turns out that not any interaction that we can write down gives rise to a consistent quantum field theory at all energy scales. Only so-called renormalizable quantum field theories do have this property that they have a finite number of couplings that really determine the theory at all energy scales. So not any possible set of interactions like this is consistent, but still many possibilities, in fact, an infinite number of possible quantum field theories do still exist and make sense. And a very specific renormalizable quantum field theory called the standard model of particle physics, with neutrino masses added, with some specific fields, including, of course, the quarks, whose existence follows from Yuval's work, and other particles, and with specific values for the 26 parameters of this model turns out to describe nature extremely well and to agree with all the experiments that were done up to today in the context of particle physics. So, of course, quantum field theory is a great success story that Yuval contributed a lot to, but it does still have several limitations, and one of them was already mentioned before. So the specific quantum field theory that describes the strong nuclear interactions, QCD, is a quantum field theory that has the property that its coupling constant is small if we go to high energies or to very short distances compared to the size of a proton, say. So in that regime, the coupling constant is small, but the coupling constant becomes large if we go to lower energies or to longer distances. And in that regime, we do not know how to solve the theory. And it turns out that in this regime, the basic fields of the theory, the quarks and the gluons, no longer correspond to particles. Indeed, we don't have any particle states corresponding to the quarks and gluons, but instead, these fields form complicated bound states like the protons, like the omega minus baryon, which is shown in this old photograph, and like mesons. And we know that these various bound states are described by the theory in principle, but in practice, we do not know how to compute their properties except by numerical evaluations of the path integral in QCD that were mentioned in David's talk. And indeed, even qualitative features of QCD, like the confinement of quarks and gluons into these bound states, are still mysterious, and we do not understand them well in this framework of quantum field theory. So that's one limitation. A second limitation involves gravity. So gravity is, of course, the main force that we feel in everyday life, and there are good arguments that it should also be quantum mechanical. However, quantum gravity effects are very difficult to measure because gravity is typically measured at long-distance scales, while quantum effects usually become important at small scales. One can use just dimensional analysis to put together the fundamental constants associated with quantum physics, gravity, and relativity to estimate at what scale quantum gravity effects become important. And we see that quantum gravity effects become important at length scales that are 20 orders of magnitude smaller than the size of a proton. So these unfortunately, these are not experimentally accessible in the foreseeable future, so we do not have any experimental ways to test or to investigate quantum gravity, but we can still analyze it theoretically and try to construct consistent theories of quantum gravity. In classical gravity, classical gravity is described by general relativity, and there gravity is described by the fluctuations of the metric of spacetime, which is just a local field. So one possibility would be just to try to build a quantum field theory description of quantum gravity using the metric as a basic field and using the action of general relativity coupled to various matter fields. But it turns out that this does not lead to a consistent theory for many reasons, but one of them is that it gives a theory that's not renormalizable, so we cannot describe it just in a finite number of parameters, so we need to do something else in order to get a consistent theory of quantum gravity. Now, string theory is a priori something completely different, and so in the 1960s, people started considering strings, one-dimensional extended objects, as the basic constituents of nature instead of using particles as the basic excitations. A string is characterized by a scale that's given by its tension, or energy per unit length, which is 1 over L string squared in my notations. Now, if we look at this, so a string is characterized by this typical length scale. If we look at strings at long scales compared to that length scale, then they look just like particles, but the string has various internal excitations that can give rise. So a single string can give rise to various different types of particles depending on its specific excitation modes. And in particular, when you quantize string, you find that you have this typical behavior that the masses squared of particles of spin j turn out to be proportional to j with this type of proportionality relation. Now, the first origins of string theory were before the discovery of QCD, and one of the main motivations for string theory was the fact that many particles feeling the strong nuclear interactions were discovered, as David described in his talk. None of them looked like they were more fundamental than others, and the spectrum of the mesons of the theory looked like the spectrum of excitations of a string, so this motivated trying to construct an alternative string theory description for the strong nuclear interactions. Of course, eventually it was discovered that when we go to shorter distance scales, these mesons and baryons all contain more fundamental particles, the quarks and the gluons, so that we can describe the strong nuclear interactions by quantum field theory, which is just a QCD. But some people still continued studying string theory, and one of the interesting things that they discovered is that when one quantizes strings, one automatically obtains a theory of quantum gravity, because one of the excitations of the strings turns out to always be, in any consistent string theory, a massless particle of spin 2, and particles of that type, like the graviton, are the objects that mediate gravitational forces. So whenever we quantize strings, we automatically get a theory of quantum gravity. And at this point, in some sense, the objectives of string theory separated from quantum field theory. So string theory was not used for many years for quantum field theory, but instead string theory became a leading candidate and perhaps our only consistent candidate for a theory of quantum gravity. Now, Yuval, of course, was very interested in quantum gravity, although, now, as far as I know, he never worked on string theory, but he did not reject it either. So, for instance, in this review paper that he wrote in 1998, he discussed various possible solutions to quantum gravity. And even though string theory is not the first one on the list, at least it does appear in fifth place on the list. So he was willing to accept at least the idea of string theory being the correct theory of quantum gravity. So I hope that his memory is not offended by me discussing string theory here. So back to string theory. So the simplest solutions of string theory that we find live in 9 spatial dimensions plus the time dimension, but we can compactify 6 of these dimensions to get theories that live in a 3-dimensional space as we see around us. It turns out that string theory has many different solutions, and we do not yet know if any of them describes our universe or not. There's really a huge number of solutions, and it's difficult to study all of them. But in all of these solutions, we do know how to quantize strings, and this does allow us to obtain a quantum theory of gravity, where we can compute, for instance, the quantum corrections to scattering of gravitons. But unfortunately, so far, we can only do it in a perturbation theory, expansion, and the coupling constant between the strings. And we do not yet have a general non-perturbative definition of string theory, analogous to the path integral that we have in quantum field theory, that would make it well-defined also for finite values of the coupling constant. So far, string theory is not yet a complete theory of quantum gravity. So this was the quick review of string theory. Now let me discuss how to put them together. So up to this point, quantum field theory is very different from string theory. Quantum field theory describes particles with various local interactions, and it has applications in the context of quantum field theory, while string theory is some non-local theory that describes these non-local excitations of strings, and that has applications for quantum gravity. But there are many different, it turns out that there are many different connections between them. One connection comes from this fact that if we have a string theory, then at short distances it's described by strings, but if we look at it from longer distances, then it can be described as a theory of particles. And for instance, the scattering amplitudes of strings that would be described by a Feynman diagram like this. If we look at it at long distances, it just becomes a Feynman diagram of particles. Now, it turns out that a single scattering amplitude of strings, when we take this long distance limit, contains many different quantum field theory diagrams, and there's a smaller number of string diagrams that we need to compute if we want to discuss a specific process. So in some cases, string theory gives us an efficient way to perturbatively do computations in quantum field theory by just first doing the computations in string theory and then taking their long distance limit. So this is one type of relation between string theory and field theory. Another application that was just mentioned in Shlomo's talk is that by considering various long-distance limits of string theory, many new quantum field theories have been discovered, including, in particular, quantum field theories in 4 and in 5 space dimensions that were not suspected before just from field theory arguments, but that can be constructed by taking appropriate limits of string theory. So these are connections where string theory teaches us about field theory. However, a deeper connection was suggested by Prof in 1974. So Prof studied SUN gauge theories, which generalize the SU3 gauge theory that appears in QCD. And he analyzed these gauge theories based on the group SUN, taking the large n limit, where the rank of this gauge group becomes very large. And what he found is that in this limit, the sum over all the Feynman diagrams that we would use in this field theory to describe, say, a scattering process and any other computations can be recast as a sum over 2-dimensional surfaces that looks like a string theory in which the string coupling, G string, scales like 1 over n. So this suggests that there could be a duality, namely gauge theories could have an alternative description in terms of some specific type of string theory, where the coupling constant is not the same in these two dual descriptions. The coupling constant of the string theory becomes small when we take this large n limit, even though the quantum field theory is still strongly coupled there. If we take these SUN gauge theories, they still confine and have various other strong coupling phenomena. But the string theory becomes classical in this limit, while in other limits, the field theory becomes weakly coupled, while the string theory becomes very complicated. So this is a general property of dualities. We have an equivalence between two very different descriptions, such that each one of them becomes simple in different regimes. Now, this idea of a tuft of an equivalence between gauge theories and string theories is a very general idea, but it took many years to realize this general idea because originally people naturally assumed that the string theories that are dual to gauge theories live in the same space-time that the field theories live in. But this runs into the problem that, as we said, string theory always gives quantum gravity. Well, of course, quantum field theory does not include gravity in it. So it took a long time to resolve this problem. And at first, only a few examples in low dimensions were understood. However, in the last 30 years, and in particular following the ADS-CFT correspondence, it was understood that quantum gravity, and thus also string theory, has a property called holography, which was already mentioned here in some previous talks. So, as I mentioned, quantum field theory is local, which means that it has local degrees of freedom at every point, and therefore the number of degrees of freedom it has in some region of space scales like the volume of that region. However, quantum gravity turns out not to have any local gauge invariant observables, and it turns out that in quantum gravity, the number of degrees of freedom that we have in some region of space actually scales like the area of the boundary of that region. This is sometimes called the Bekenstein bound, rather than like the volume of that region. So this general property of quantum gravity suggests that perhaps a quantum gravity theory living in d space dimensions could be equivalent to a standard quantum theory that lives in d-1 dimensions, because both of these theories would have the same scaling of the number of degrees of freedom as we increase the region of space that we consider. And this property has interesting implications both for quantum gravity and for this relation between field theory and string theory. So starting from quantum gravity, what this property implies is that the three-dimensional space that we see around us is probably just an approximate emergent description that is only valid at long distances, or long here, of course, means long compared to this very tiny Planck scale, but still long distances. Just like a hologram is a two-dimensional surface that looks like it's three-dimensional, but it's actually two-dimensional. Unfortunately, we don't know yet what is the fundamental description of quantum gravity in flat Minkowski space or in cosmological backgrounds, and this is still a very active topic of research. But we do understand how to, so quote-unquote, decode this hologram for quantum gravity living in other spacetimes, and in particular in specific constant negative curvature hyperbolic spacetimes called anti-de Sitter spacetime. And in the context of the relation between quantum field theory and string theory, what this holographic principle implies is that the strings theory that is dual to some given quantum field theory should actually live in one extra space dimension, because then the quantum gravity can live in this higher dimensional space that fluctuates, but whose number of degrees of freedom scales with the area of that region, while the quantum field theory needs to live on a fixed spacetime. And in these examples, this is realized by having a boundary of the space which is infinitely far away and which does not fluctuate, so that it can be equivalent to the space that the quantum field theory lives on. So in this way, we can find many examples of this duality between string theory and quantum field theory that utilize this holographic principle by having the string theory live in a spacetime that has one extra spatial direction or more. So by now we have many examples of these dualities, both for confining gauge theories and for scale invariant gauge theories. The string theories are usually best understood in the case where the strings move in a weakly curved space, and that turns out to correspond to quantum field theories that are strongly coupled and also approximately supersymmetric. So let me now summarize what's the current status of this relationship between quantum field theory and string theories. So for the various examples that we have of theories that have both the gauge theory description and a known string theory description, string theory and quantum field theory are no longer rival descriptions, but they're just duals of each other. Some aspects of the theory are easier to see in the gauge theory description, while others, for instance, confinement and other strong coupling phenomena, are easier to see in the string theory description. Of course, in the string theory description, the strings connect quarks and antiquarks if we try to separate them, so it becomes completely manifest that the quarks are confined. Moreover, in these cases where we have a duality of this type, the quantum field theory provides for us a non-perturbative description of quantum gravity. And a nice thing about this description is that it is manifestly unitary, guaranteeing that black hole formation and evaporation are unitary processes, even though the details of exactly how the information emerges from evaporating black holes and what happens to observers falling through the horizon are still not completely clear. A major challenge is still to find the specific string theory which is dual to QCD, And even in this large unlimit, so I mentioned that in the large unlimit of an SUN Young-Mills theory, say, then this is supposed to be described according to this duality by just a classical string theory, whose string coupling goes to 0. But unfortunately, we still don't know how to construct the string theory, which is dual to large Young-Mills theory, and therefore also to the large unlimit of QCD. The basic objects of the string theory are supposed to be the electric flux tubes or chromoelectric flux tubes that connect quarks and antiquarks. And we do know that the string theory is a very complicated one and lives on a highly curved space. And it is a major challenge to find it. And this would give us a description, an equivalent description of QCD, in which confinement will be manifest, but perhaps other properties of the theory will not be manifest. As I mentioned, we do know how to describe the string theory duals of other confining theories. In particular, there are even examples that are continuously related to QCD, but all of these examples have some extra degrees of freedom, and we still don't understand how to get rid of these extra degrees of freedom and find a string theory which is just dual to QCD. And one of my current topics of research is finding duals for versions of QCD in lower dimensional spaces, such as Young-Mills theory in 1+1 dimensions and Young-Mills theory coupled to quarks or to fermions and adjoint representation. So hopefully these toy models will have a simpler relation between field theory and string theory and will provide us a first step towards going to higher dimensions. Now, well, one problem is, of course, that in general, we don't know how to construct the string theory, which is dual to any specific quantum field theory that we would like to describe. But we can understand some general properties that the string theory dual to QCD should have. For instance, one property is that we know that if we go to long distances, then the flux tubes of QCD should just describe smooth string world sheets, and we should have some smooth description of the world sheets. However, because at short distances, QCD is asymptotically free, and it's described just by free quarks and gluons, we know that if we look at these strings at very short distances, where the quarks and gluons are weakly coupled, then the same strings should behave like a collection of particles that are only very weakly bound to each other. So these are some general properties that the string theory dual to QCD should have, and it is a challenging property to construct string theories that have this property. Now, we still don't know if there is any, so that's in the context of the first limitation of quantum field theory that I mentioned, of trying to understand strong coupling physics using string theory. So we do believe that in principle, there should be some string theory dual to QCD. We know some of its properties, but unfortunately, we do not yet know precisely which form it takes, and it is still an interesting challenge to compute it. As to the second limitation, namely quantum gravity, we still don't know if there is any solution of string theory that describes quantum gravity in our universe, and which one. So again, there are many different solutions of string theory. Many of them look very similar to our universe, so it is plausible that one of these solutions does describe our universe, but we still do not know which one it is and how to find it. And more generally, even though we do understand well quantum gravity in some spacetimes, like these anti-de Sitter spacetimes that I mentioned, we do not yet understand well quantum gravity in Minkowski space or in cosmological spacetimes, and this is still, again, a very active research program. However, we do understand quantum gravity now in many cases where it is dual to quantum field theories, and understanding quantum gravity in these cases is teaching us more and more about various fundamental aspects of quantum gravity, such as its relations that we heard about in Shira's talk to quantum information and quantum chaos. And hopefully, this better understanding that we are gradually obtaining of quantum gravity will eventually help us to formulate also quantum gravity in our universe. So this was a quick summary of our understanding of field theory and gravity 40 years later. So thank you for listening.
Okay. So thanks very much to Ofer for a beautiful and guided tour, like visiting the Louvre in an hour.
Well, in 20 minutes. Yes, people do that.
Okay, David, please. Microphone, please. Here, the second row. Yes, please.
Well, that was a magnificent survey, and I commend you for doing it so quickly.
David, I think the microphone is...
I know. Doing it so quickly, but if I've been able to follow your example earlier, I would have gotten close to the end of this talk. And I would have brought up sort of the question I'm asking. So, by the way, you say in your perspective, as many of them but one question, is whether, and it also sort of motivated my students, sort of feel that we have the elements of this general framework, string theory, field theory. There's a lot to understand, but it's conceivable that we or grandchildren will, and that'll be it. But we could be totally wrong, because as I remarked that the development of quantum mechanics was lucky because the hydrogen atom was so simple. Development of this theory of gravity was lucky because the solar system was very simple to these two bodies. The development of string theory was so simple because the simplest strings theories were essentially free two-dimensional field theory. We could be missing something totally different. All the new innovations that we could never easily get.
Right.
I suspect.
So let me split the answer into these two parts of my talk. I mean, so in the context of, say, string theory for QCD and understanding field theories, in that context, I think we are on solid ground, and I think we have every reason to believe that there is a two-dimensional worldsheet that describes QCD. And also, for our understanding of quantum field theory, I think we do have a good understanding of quantum field theory, and corresponding to that, we do have a good understanding of quantum gravity in specific spacetimes, at least, that we do understand. But of course, quantum gravity being highly non-local, understanding it in one spacetime is far from guaranteeing that we can also understand it in other spacetimes, like in Minkowski space or de Sitter space or anything like that. And it's certainly highly plausible that that these examples are misleading us, and that to understand quantum gravity in other spacetimes, new tools are required. I mentioned some of these new tools here, but possibly we need very completely different tools. So I have nothing smart to say about that, except to continue working on the tools that we have and developing new tools, and we'll see. So the jury's still out.
Eliezer, please. Microphone. Maybe you stay here with the microphone. Okay.
Okay, actually, it's not a question, but an answer.
Even better.
You asked about Yuval's attitude towards string theory.
Yes.
So in page 19 of the, not of your talk, but in page 19 of the interview, you will find that he has a very positive
Yes, I read that too, yes. But I think that this is even more positive, because here he really lists these 5 possible resolutions of quantum gravity, and string theory is number 5. I saw in the interview that he emphasized that there are great researchers in Israel in string theory, which is true. But here it's a more physics comment that he's really willing to accept it as a theory.
I would disagree with you, because here it's the only thing he mentions.
Okay. Yes.
What's the time ordering of the interview and this?
The interview was later. This was in 98, yes. So the interview.
And when is this?
2000.
2003.
Yeah.
Okay. So clear, monotonic. Thank you, Eliezer.